The Committee on Science, Space, Technology, Subcommittees on Environment, and Subcommittee on Energy joint hearing on Geoengineering, Innovation, Research, and Technology is called to order. Without objection, the Chair is authorized to declare recess of the committee at any time, and I now recognize myself for 5 minutes for an opening statement. Good morning, and welcome to the Joint Environment Subcommittee and Energy Subcommittee hearing on geoengineering. I thank each of our witnesses for being here today. And since this is the first time we're discussing the topic of geoengineering this Congress, it is important to explain what geoengineering actually is. In its simplest terms, geoengineering is the concept of using scientific understanding to alter the atmosphere in a way that produces positive outcomes and results. Many of the concepts in this field deal with solar radiation management or how to influence the effects of the sun on the Earth. But the field is by no means limited to solar research. Geoengineering can also be used to manipulate different levels of gases in the atmosphere, such as carbon dioxide. These avenues of geoengineering research and others are still in the early developmental stage, and any or all of them may warrant further exploration. While there are at least a few programs in our nation's universities that are looking into these concepts, federal research is still limited. However, if in the future the government wants to actually apply the concepts and findings of geoengineering research, we must fully examine both the potential merits and potential pitfalls of this emergent field. Since the theories and concepts involved are still so new, we cannot say definitively if geoengineering technology warrants full-scale development or deployment. Quite simply, more basic research is necessary to determine whether it is a viable tool. And today we will learn about what research has been conducted on geoengineering and which promising concepts should be explored further. We will hear from government, academia, think tank, and industry representatives who have unique perspectives on this topic. They will tell us about the research being done, as well as future concepts and how they could be used responsibly. We as lawmakers have a responsibility to explore these concepts, learn as much as possible about them, and discuss ideas about how we can be helpful in supporting basic research. I'd also like to take a moment to clarify any mischaracterizations about this hearing. The purpose of this hearing is to discuss the viability of geoengineering and any early-stage research associated with this approach. The hearing is not a platform to further the debate about climate change. We've had lots of that this session. Instead, its aim is to explore approaches and technologies that have been discussed in the scientific community and to assess the basic research needed to better understand the merits of these ideas. It is my hope that members will respect this focus so that we can have a meaningful discussion about geoengineering. Again, I want to thank the witnesses for being here today, and I look forward to hearing more about these interesting concepts. With that, I yield back my time and recognize the ranking member, Ms. Bonamici, for her opening statement.
Thank you very much, Mr. Chairman, and thank you for holding this important hearing. I'm very encouraged that the Science Committee is discussing geoengineering, a field of science and engineering that is still in its infancy and has ample areas for future research. And it's noteworthy for its potential. It's also important that we consider it from political, ethical, legal, and environmental perspectives. Geoengineering is a set of climate interventions that aim to manipulate our climate to either remove greenhouse gases from our atmosphere or reduce the amount of sunlight absorbed by the Earth. Now, some may argue that geoengineering is a way to use technology to bypass important mitigation and adaptation strategies that address the impacts of climate change. But even with geoengineering, our first and primary actions to address climate change must be mitigation and adaptation strategies. In our communities, climate change is not a partisan issue. Nationwide, there are fishers and farmers and small business owners and servicemen and women who are having to change the way they do their jobs because of climate change and regardless of their political affiliation. The economic, health, and environmental consequences of climate change are well known, and our understanding about how to address the causes of climate change continue to improve. It's critical that we support scientific research about climate and that we build on rather than break down decades' worth of progress on this issue. I urge the committee to hold hearings specifically on mitigation and adaptation strategies to help communities grapple with the situation. Geoengineering is an option our country should explore. The state of current geoengineering research makes clear that we are years or perhaps decades away from potential deployment, and the risks of deployment are not well understood. We're hoping for some answers here today. In fact, a key finding in the U.S. Global Change Research Program's Climate Science Special Report, which was just published last Friday, determined that further assessments of the technical feasibilities, costs, risks, co-benefits, and governance challenges of climate intervention or geoengineering strategies, which are as yet unproven at scale, are a necessary step before judgments about the benefits and risks of these approaches can be made with high confidence. This is because of a lack of technical maturity and understanding of the risks associated with geoengineering. We do not currently have enough evidence to determine whether any of the various proposals for geoengineering can provide long-term solutions to address the impacts of climate change, or that they would not pose any adverse consequences to our environment. Our climate is changing, and the warming trends observed over the last 100 years are primarily caused by human activities, specifically the emission of greenhouse gases. In fact, this is one of the most prominent findings in the Climate Science Special Report. This report unequivocally lays out the need to reduce carbon dioxide emissions to prevent long-term warming and short-term climate change. I want to ask the subcommittee chairman for unanimous consent to include a letter addressed to him and Chairman Smith into the record. It's been signed by many prominent members of the geoengineering research community, highlighting the urgency of the threat that climate change poses and re-emphasizing that geoengineering is not a magic fix to addressing climate change.
Without objection. And
with that, Mr. Chairman, I'd like to yield the remainder of my time to the gentleman from California, Mr. McNerney.
Mr. McNerney, please.
Well, I thank the gentlewoman from Oregon, and I thank the chairman for holding this hearing. Climate change is happening, and the effects are accelerating faster than the scientific models predict. The changes we are experiencing today are the results of heating that has taken place over the past decades. Meanwhile, carbon concentration in the atmosphere is continuing to increase. Therefore, additional heating and climate impacts are inevitable even if we were to stop carbon emissions immediately. In other words, we are committed to significant change. The unknown is how much change we're committed to and how fast it will take place. It's not known if we are committed to truly catastrophic change with the current policies or not. But no matter what, it's absolutely critical to reduce carbon emissions and prepare for the changes that are coming. In other words, mitigate and adopt. The changes we are committed to may be so strong that we will need to know what can be done to prevent utter catastrophe. What tools are available? What are the technical feasibilities? What are the costs? And what are the risks of the different approaches to avoiding catastrophic change? That's where this hearing comes in. What are the hypothetical alternatives, and how do we best go about determining their feasibility, costs, and impacts? I will be dropping a bill next week, which members of the panel have already seen, and I need guidance from experts on what changes to the proposed legislation is needed. Thank you. I yield back.
Thank you. I now recognize the chairman of the entire committee, Chairman Smith.
Thank you, Mr. Chairman, and I also thank Congressman Weber for letting me give my opening statement before him. I have a markup that began in the Judiciary Committee that unfortunately I've got to attend, but I hope to be back shortly. Mr. Chairman, first I want to thank the Chairman of the Environment Subcommittee, you, for having this hearing, and also Representative Weber of Texas, the Chairman of the Energy Subcommittee, for your interest in this subject. Also want to thank the gentleman from California, Mr. McNerney, for his persistent interest in this subject. Every time I've seen him on the House floor for the last couple of months, he's wanted to have this hearing, so we appreciate his interest as well. Mr. Chairman, geoengineering's potential is worth exploring. Generally, we know that the technologies associated with geoengineering could have positive effects on the Earth's atmosphere. These innovations could help reduce global temperature or pull excess greenhouse gases out of the atmosphere. For instance, one of the most intriguing ideas in this field is solar radiation management. This concept involves finding innovative strategies to reduce the amount of sunlight that reaches and warms the Earth. Today, one of our witnesses will expand on this idea with a concept that brightens clouds and reflects sunlight, which is measured in albedo. While this technology is interesting, we have a lot to learn. Some have questioned the unintended consequences of geoengineering. One concern is that brightening clouds could alter rain patterns, making it rain more in some places or less in others. Such technologies could drastically reduce global temperatures in the future by spraying aerosols into the atmosphere to reflect sunlight. While we are not sure this is plausible, some scientists believe it could achieve substantial environmental benefits at a cheaper cost than regulations. Regardless of these claims, we still do not know enough about this subject to thoroughly understand the pros and cons of these types of technologies. As the climate continues to change, geoengineering could become a tool to curb resulting impacts. Instead of forcing unworkable and costly government mandates on the American people, we should look to technology and innovation to lead the way to address climate change. Geoengineering should be considered when discussing technological advances to protect the environment, and geoengineering should not be ignored before we have an opportunity to discover its potential. This hearing will help Congress do just that. Mr. Chairman, I thank our witnesses today for testifying on the current state of geoengineering research and for their recommendations about how to advance practicable efforts in this area. And I'll yield back.
Thank you, Mr. Chairman. I now recognize the Chairman of the Energy Subcommittee, Mr. Weber, for an opening statement.
Thank you, Mr. Chairman. Let me add my welcome to today's joint Environment and Energy Subcommittee hearing. Today we are going to hear from a panel of experts on the status of America's research in geoengineering, a field truly in the scientific unknown. Hearings like today's help us remind us of the Science Committee's core focus, the basic research that provides the foundation for technology breakthroughs. Within the DOE lab system, Pacific Northwest National Lab is leading the effort to explore the potential impact of geoengineering technology. PNNL hosts geoengineering researchers who hope to open the dialogue on this groundbreaking technology, Jerry, you'll be glad to hear, and consider what methods could have the most positive impact on the climate. Some proposed ideas at PNNL include placement of mirrors in space, injection of naturally occurring substances into the atmosphere to mimic a volcanic eruption, or brightening the clouds overhead. All of these methods could have a cooling effect on our lower atmosphere. It's amazing to think that molten lava from volcanic eruptions can actually produce compounds that cool the air. Brightening clouds is equally interesting, but only early-stage evaluation has occurred on the practicality of this approach. As we will hear from one of our witnesses, we have already seen ship tracks that create this brightening effect where the sunlight is actually reflected back into the atmosphere. By injecting aerosols composed of seawater particles into low ocean clouds, researchers could shrink the size of water droplets and in turn brighten those clouds. PNNL's climate and earth systems science researchers and partnerships have to rely on computer models to understand the potential impact of these very basic geoengineering methods. But as we've heard before in this committee, models are only as good as the data they use. I believe that we should consider funding appropriately scaled field testing to improve the accuracy of geoengineering models. Through the national labs, the U.S. already partners with researchers from Canada, China, Denmark, Germany, Japan, and Norway. These scientists use the output from 12 climate models in the Geoengineering Model Intercomparison Project, which seeks to understand the possible climate effects of geoengineering. Geoengineering has the potential to provide us with a whole new understanding and approach to atmospheric research. If we put aside the debates about climate change, we can support innovations in science that create a better prospect for future generations. The federal government should prioritize this kind of basic research so we can not only understand the science of geoengineering, but hopefully partner with the private sector to develop technology to mitigate changes in climate. When the government supports basic research, everyone has the opportunity to access the fundamental knowledge that can lead to the development of future technologies. The future's bright for geoengineering, and I want to thank our panel of witnesses for testifying today. I look forward to a productive discussion about the innovation, research, and technology of this emerging field of science. Mr. Chairman, I yield back.
Thank you, Mr. Weber. I now recognize the ranking member of the Energy Subcommittee, Mr. Vesey, for an opening statement.
Thank you, Mr. Chairman. And we have an excellent panel of witnesses today, and I'm really looking forward to hearing their insights. And thank you very much for being here. Despite the numerous claims, geoengineering is not the answer to 150 years of polluting our planet at an unsustainable rate. And in order to slow the impact of climate change and eventually reverse its effect, we have to get our priorities straight, and mitigation and adaptation must be part of the top priorities. We must face the global challenge of climate change, and solving this challenge requires every nation to find effective solutions to reduce our emissions and set us on a far more sustainable path. The scientific community has made clear that climate change will continue to be an issue for the rest of this century and beyond. The long-term nature of this challenge is the reason we need to investigate every possible solution in addition to implementing mitigation and adaptation strategies. Geoengineering, in particular, is in its very early stages, and more research is required to expand our understanding of its risk and potential benefits. During our discussion today, I hope the witnesses can provide us with their recommendations on what types of research the federal government should invest in for the benefit of all Americans. These recommendations will help shape our national investments in climate modeling, Earth systems research, laboratory experiments, and potential small-scale field tests in the coming decades. On that note, I would like to stress to my colleagues the importance of supporting the full spectrum of research at the Department of Energy. In particular, activities within the Office of Sciences, Biological, and Environmental Research Program are crucial to expanding our knowledge of Earth systems and climate modeling. Funding this important research can have numerous benefits, including advancing the field we are discussing today. Funding this important, it is unfortunate that the Trump administration's budget proposal included a 43% cut to BER, with major cuts and outright eliminations of key activities within the Earth and Environmental Systems subprogram. These cuts would hurt the emerging field of geoengineering, but more importantly, they would cripple our ability to understand the range of factors driving global temperatures upward. If you are a climate skeptic, then you must support more research to expand our collective understanding. If you cannot support that fact, then you are choosing to ignore the facts. Frankly, we have no time to ignore the mounting scientific evidence as it relates to climate change. We need productive dialogue if we want to better understand this challenge and embrace the necessary solutions. In addition to supporting the key research activities that underpin geoengineering, there may also be additional federal investments that Congress should consider in order to have an impact in the near future. Carbon dioxide removal strategies are a generally less risky form of climate intervention that may prove useful in our efforts to fight the impacts of climate change. These strategies come in the form of bioenergy with carbon capture and sequestration, direct air capture technologies, enhanced geological weathering, and land use management, just to name a few. The National Academies examined carbon dioxide removal in 2015 and concluded that this area is ripe for further federal research investments. For this reason, I included this critical research in a draft bill that I will be introducing in the coming weeks, the Fossil Energy Research and Development Act. In addition to authorizing key R&D activities for carbon capture, utilization, and sequestration activities, the bill would also instruct DOE to create a research program on carbon dioxide removal. I hope that my colleagues on both sides of the aisle will join me as a co-sponsor of this legislation. The bill will push the DOE to prioritize the important work of environmental mitigation within the Office of Fossil Energy. The public health and economic benefits are considerably numerous. I hope this bill can be bipartisan path forward to an area of research at DOE that needs it. I look forward to working with my colleagues on these issues, and thank you, Mr. Chairman. I yield back the balance of my time.
Thank you, Mr. Vesey. Let me introduce our witnesses. Dr. Phil Rasch. Our first witness today is Dr. Phil Rasch, Chief Scientist for Climate Science and Laboratory Fellow at Pacific Northwest National Laboratory. Previously, Dr. Rasch served as a chair of the International Global Atmospheric Chemistry Program and was named a Fellow of the American Association for the Advancement of Science. He received a bachelor's degree in atmospheric science and chemistry from the University of Washington and a master's of science in meteorology from Florida State University and he completed his PhD at the National Center for Atmospheric Research in Boulder, Colorado. Our second witness is Dr. Joseph Majkut, Director of Climate Policy at Niskanen Center. Previously, Dr. Majkut worked as a Congressional Science Fellow under the American Association for the Advancement of Science and the American Geoscience Institute. Dr. Majkut received degrees from Princeton University, the Delft University of Technology, and Harvey Mudd College. Our next witness is Dr. Douglas MacMartin, Senior Research Associate at Cornell University. Previously, Dr. MacMartin led the Active Control and Flow Control research programs at the United Technologies Research Center. He received his bachelor's degree from the University of Toronto and his PhD in aeronautics and astronautics from MIT. And our last witness today is Ms. Kelly Wanser, Principal Director at Marine Cloud Brightening Project, Joint Institute for the Study of the Atmosphere and Ocean at the University of Washington. Ms. Wanser is a member of the National Academies of Sciences. She received her bachelor's degree from Boston College and her master's degree from the University of Oxford. I now recognize Dr. Rasch for 5 minutes to present.
We ready?
We're going to keep discussing here for a few minutes. No, I think we're now ready to recognize Dr. Rasch for 5 minutes to present his testimony. Thank you, Dr. Rasch.
Thank you. Chairman Biggs and Weber and Smith, members Bonamici and VC and subcommittee members, thanks for the opportunity to be here. I testified before this committee in 2010 on geoengineering. I'm the chief scientist for climate science at Pacific Northwest National Labs, where I lead programs studying the Earth's atmosphere and environmental change. I've also been involved in geoengineering research. I've authored about 20 papers on geoengineering, supported mainly by philanthropic foundations and the NSF in my previous job. I was also a member of the committee that wrote the recent National Research Council report on geoengineering and a lead author on relevant chapters from the Intergovernmental Panel on Climate Change report as well. Americans have become increasingly aware of changes in our environment, ranging from dramatic decreases in sea ice in the Arctic to increases in summertime heat waves, droughts, floods, fires, and damage from hurricane and other extreme weather events, including increasing ocean acidity that damages fisheries. Evidence in the National Climate Assessment and elsewhere indicates that the changes are connected to increases in carbon dioxide. So a prudent step to reducing impacts is to stop increasing carbon dioxide as quickly as possible. Geoengineering methods attempt to address some of these threats through two very different strategies. I'm not an expert in the carbon dioxide removal strategy you heard about earlier, so I won't discuss it further. And I'll sometimes talk about solar radiation management as sunlight reflection methods, a term I prefer. Sunlight reflection methods try to reflect some of the sun's energy back to space, cooling the planet. Two strategies have received the most attention, so I'll focus on those. One method is called marine cloud brightening. You'll all have felt the surface temperature go down when a cloud passes overhead on a hot summer day by reflecting sunlight back to space. This is how clouds cool the planet. We know clouds can be further brightened. One dramatic example occurs when ocean freighters add particles below clouds to change them and form bright ship tracks. Marine cloud brightening attempts to mimic that kind of cooling by introducing sea salt particles below clouds. Stratospheric aerosol geoengineering tries to mimic the cooling effects of large volcanic eruptions by placing extra particles in the upper atmosphere. Let me just cover a bit of what we know and don't know and then make some recommendations for progress. There's a lot more detail in my written testimony. We know it's still early days for SRM research, but there are hints it could help address climate change by offsetting, delaying, or slowing warming. Hints are that will help counter other changes as well. We think SRM could buy time for other measures to be put in place. Even if it works, though, we know it won't be a magic bullet. It won't compensate for all problems, and it may have side effects. Stratospheric aerosol geoengineering and marine cloud brightening have some common features, but they're different, with different risks and impacts to the planet. If we used geoengineering, it would need to be adjusted to balance the excess carbon in the atmosphere, and we think it would be very risky to balance a lot of carbon dioxide. We don't yet know whether geoengineering should be a part of the strategies addressing climate change. It'll take at least a decade to sort out the benefits, risks, and trade-offs associated with these different technologies. So what should we do? I think it's time for a coherent and goal-oriented geoengineering research program that complements ongoing research in Earth system science, but focuses on a defined set of objectives targeting better understanding of the effectiveness and potential risks associated with specific geoengineering techniques. That program should include modeling, lab studies, small-scale field studies, and technology development, in addition to addressing societal needs for transparency and governance. Small-scale field studies are needed. These studies should be far too small to affect climate, but they'll help us understand the processes important to the SRM strategies and also help answer crucial questions for climate science. I discuss one example in my written testimony. I believe it's urgent to have a review and governance strategy for this program to help with public understanding and engagement and to improve safety. Thanks, and I'm happy to take questions.
Thank you, Dr. Rasch. And now I will recognize Dr. Majkut for 5 minutes to present his testimony.
Thank you, Chairman Biggs and Weber and Ranking Member Bonamici and members of the committee. It's grateful for the invitation to join you today. My name is Joseph Majkut, and I'm the Director of Climate Policy at the Niskanen Center here in Washington, D.C., where my work focuses on research into climate and energy issues, and my personal area of expertise is climate science. There is no practical scientific doubt that human activity is contributing to climate change, nor that continuing emissions will lead to more warming. There is, however, a great deal of uncertainty about the extent of future warming and its environmental and economic consequences. Given that uncertainty, we should think about this as a risk management problem. There may be no perfect solution. But in general, we should seek ways to reduce greenhouse gas emissions, minimize societal vulnerability, and otherwise limit the potential costs of a warming planet. Geoengineering may be one such tool to address those potential costs. Further research, judiciously done, will help us answer that question. With that in mind, I would like to emphasize 3 points from my written testimony. The first is that there is a great deal of uncertainty about whether or not geoengineering would work in practice. By changing the reflectivity of the high atmosphere or brightening clouds, we might be able to offset some degree of global warming quickly and reduce its attendant effects, but the risk of unintended consequences might be large. We do know that once we start cooling the planet by artificial means, stopping will be followed by rapid warming as long as CO2 levels remain high. We also know that a geoengineered world could not simultaneously hold temperatures, rainfall, and weather patterns static, meaning that there will be trade-offs should geoengineering ever be used to partially or completely offset global warming. The second is that developing a better scientific understanding of those potential trade-offs justifies ongoing and future research. Whether or not each of us is concerned about the risks of climate change or repulsed by the very idea of geoengineering, changes to the Earth's climate will inevitably force future generations to confront such choices. This research will be affordable and need not supplant other efforts to understand the nature of climate change. Such research will occur in supercomputing facilities, at the lab bench, and also in small-scale field experiments. I'll add that I hope it will also be approached via the social sciences, as judgments of whether or not geoengineering is good or practical are not consigned to questions of chemistry or physics. Both the 2015 report from the National Research Council and the most recent update of the U.S. Global Change Research Program Strategic Plan highlight the importance of this research and complementary observational and theoretical work in climate science, especially since other countries or private actors might start intervention experiments of their own. Lastly, Congress should consider what regulatory governance structure will maximize innovation and scientific progress while protecting the public and environment from ill-informed experiments or premature deployment of these technologies. Under the 1971 Weather Modification Act, experiments intent on altering the weather or planetary albedo are already regulated, and those regulations currently require that researchers report their activities to NOAA before and after working in the field. For today, that is enough. No one, to our knowledge, is set on large experiments in the near future. However, regulatory governance should grow as experiments grow larger, and it is not clear at present how such regulations might look. Our research at the Niskanen Center indicates that small-scale experiments should be subject to little more than reporting requirements and existing environmental protections, because their climatological effect will be vanishingly small. However, Congress may want to consider if intermediate-scale experiments should be subject to prior approval of an agency, and if large-scale experiments subject to the express permission of Congress itself. How we define small, medium, and large is a question that will require further thought and should involve the input of the scientific community and civil society. A well-defined and stable regulatory structure will publicly clarify research progress and intent, and that intent should be to clarify the questions of how geoengineering might work and what the costs and benefits of doing it may be. That information could be used by future policymakers to avert trillions of dollars in losses. If the worst-case scenarios of global warming come to pass, these technologies could be used to help people, saving lives and economies from the most severe effects of climate change. Even if emissions reductions happen quickly, future generations may still find limited geoengineering of use. Managing the risks of climate change is not easy, but it will be an ever-present task in the 21st century and beyond. Research into these technologies is an important part of that task, as are adapting to warming and reducing emissions. A sturdy ship and a well-plotted course are no substitute for a close watch on the waters ahead, nor lifeboats if we need them. Thank you for the opportunity to speak to you, and I look forward to your questions.
Thank you, Dr. Majkut, and I apologize for mispronouncing your name earlier. I apologize. I now recognize Dr. MacMartin for 5 minutes to present his testimony.
Thank you. So I want to start by thanking the committee members for the opportunity to testify today. So I'm Douglas MacMartin at Cornell University with a background in both engineering and climate science, and I've been working on geoengineering for about the last 10 years. And I think one of the striking things about this panel is actually how broad our agreement is likely to be on almost all of the issues. So the reason we're all here, of course, is that, as was reaffirmed last week by the U.S. National Climate Assessment, we know that the Earth's climate is changing as a direct result of human emissions of greenhouse gases, and we know that the U.S. is already experiencing some impacts as a result. While these impacts may be manageable today, they will continue to grow so long as we continue to emit greenhouse gases, and so the less we emit, the lower the risk. And nothing we say here today about geoengineering changes the fact that we must reduce our greenhouse gas emissions and that this effort remains the most important component of a strategy to respond to climate change. That said, geoengineering approaches could become a valuable additional components of an integrated strategy to manage climate impacts. So carbon dioxide removal can effectively produce negative emissions, but we need research there on scalability, cost, and local impacts. And I'll focus primarily on the sunlight reflection or solar geoengineering side. So ideas like adding aerosols to the stratosphere or making marine boundary layer clouds more reflective. And I'd say from the limited modeling research that we've done to date, it's plausible that a limited amount of solar geoengineering used in addition to cutting emissions could reduce some of the impacts of climate change, but there's still considerable uncertainty into the side effects and risks, and that will require focused, goal-oriented research that could take decades, at least a decade, maybe more, which is why it's important to start it soon. So it's important to stress at the outset that solar geoengineering cannot be a substitute for cutting emissions for several reasons. So this conclusion has been reached by every assessment of this technology, including by the National Academies in 2015. So first, it does not compensate all of the impacts of climate change, so ocean acidification would continue unchecked. Second, if we keep adding greenhouse gases to the atmosphere, we'd have to continually increase the amount of geoengineering we were doing, so keep adding more and more aerosols to the stratosphere every year just to keep temperatures in balance, and that would lead to increased side effects and risks. And third, because of the long lifetime of carbon dioxide in the atmosphere, if we relied only on solar geoengineering, that would lead to a practically indefinite commitment to future generations to either continue deploying it or accept the consequences of high CO2. However, as long as it's considered as a supplement to cutting emissions, then it might reduce some climate damages, and so it would be valuable to conduct the needed research. A coherent, prioritized research effort needs to be driven by the end goal of supporting informed decisions regarding these approaches, and research would need to be integrated into the overall U.S. climate science research effort and should include explicit attention to research governance. The next step is probably to clearly articulate research needs and how to address them. And this might benefit, for example, from an expert body like the National Academies. For stratospheric aerosol injection, we know that it works at least for a degree or two of cooling, works in the sense of cooling the planet, simply by analogy with what happens after large volcanic eruptions. And the observations made after eruptions have helped calibrate our climate models. Near-term research here is likely to continue to be primarily model-based, and once we better understand the uncertainties we need to address, it's likely we would need some outdoor experiments to resolve key uncertainties, but I should emphasize that these would always be at a very small scale. Marine cloud brightening would also benefit from small-scale controlled experiments, which would also help inform critical uncertainties in climate change science. All of this research will build on continued investments in climate modeling, in high-performance computing, and in our ability to collect observations about the Earth system. So in summary, I, and I think many of my colleagues in the research community, believe that even with our best efforts at mitigation, the risks of future climate change are sufficiently concerning that we may need to consider all of the options at our disposal. I conclude that it's essential to conduct focused, goal-oriented research to support informed decisions, but reiterate that this needs to be in addition to the work of reducing our emissions of greenhouse gases and not a substitute. And thank you, and I look forward to all of your questions.
Thank you, Doctor. I now recognize Ms. Wanser for 5 minutes for her testimony.
Thank you. I should have some slides. Thank you, members of the committee. It's an honor to be here, and I commend you for taking up this challenging topic. My name is Kelly Wanser. I spent 20 years as an executive and entrepreneur in the technology industry, focused on understanding and securing large, complex systems. 10 years ago, I became interested in how we might apply technology to risks in the Earth system and helped form a collaboration that became the Marine Cloud Brightening Project. I'm now its program director. Prior to that, I served as an advisor to the Laser Inertial Fusion Energy Program at Lawrence Livermore National Laboratory and as senior advisor to Ocean Conservancy, looking at ocean climate risk. I'm here today because increased heat in the atmosphere poses risks to our way of life and critical parts of nature we rely on. We may require options for directly reducing heat in the Earth system. There is a need and an opportunity for innovation, and there are important steps we can take in developing a research program. Small particles, aerosols, and the way they interact with clouds to reflect sunlight are one of the primary ways that nature keeps our planet cool. The most promising approaches to rapidly reducing heat in the climate involve adding particles to the atmosphere to slightly increase this reflective effect. One approach to reducing heat, marine cloud brightening, next slide, would use sea salt mist sprayed from ships to brighten clouds over the ocean. Next slide. Applied to a fraction of all marine clouds, it might offset 2 degrees of warming globally. And the way that particles brighten clouds and cool the system is a gap in our ability to forecast weather and climate. And in this way, research in marine cloud brightening may be of strategic importance to emergency preparedness, national defense, and many industries. Today, we lack technical capabilities and scientific knowledge for marine cloud brightening or any proposed approach to rapidly reducing heat in the Earth system. Next slide. Delivering aerosols with the right properties at sufficient scale is a hard engineering problem and takes time. Next slide. Once we have technology, next steps are to build a system to enable small-scale field experiments to determine whether these ideas are feasible and basic processes to input to models. There's a well-defined research plan that starts with land-based testing, moves to single ship studies, and finally to misting one region of clouds to determine brightening effects. This research plan will take years. Satellite, next slide. Satellite, aerial, and surface observations are critical, and we will want to support our current infrastructure as well as leverage disruptive new technologies in remote sensing from innovative companies like Saildrone, Aspire Aerospace, and others. The work will also require significant advances in modeling and data analysis and increased computing capacities to support assessment and prediction of effects. It will take a decade of core technology development and basic science to determine if any options are feasible, and another decade to scale capabilities for readiness. Work must commence soon to produce knowledge and options within a time frame relevant to climate risks. With changes occurring around the world, it is likely, and may be inevitable, that others will develop capabilities. With the potential to produce geographically variable climate outcomes, the U.S. has a security interest in understanding and controlling them. Taken alone, capabilities for reducing heat in the atmosphere are not a solution. They should ultimately be considered as part of a portfolio within a management framework that includes emissions reduction, greenhouse gas removal, land and ocean management, industrial practices, economic incentives, and adaptation. Given the magnitude and urgency of the problem and our current lack of knowledge and capabilities, defining a research agenda and developing funding pathways for research may be critical. A National Academy study to help define a research agenda and establish a governance framework for research activities may be a valuable initial step. Next slide. This type of work is not unprecedented. In 1934, the US government undertook the largest effort to address an environmental problem in our nation's history, planting 220 million trees through the center of the Midwest to address the Great Storm of the Dust Bowl. Now may be the time to research the possibility of shelter belts in the sky.
Thank you. I thank each of the witnesses for your very interesting testimony. I recognize myself now for 5 minutes for questions. Dr. Rasch, I understand that most of the federal research on the topic of geoengineering has been conducted at our federal labs. Can you elaborate on how much funding is currently slated for this type of research?
To my knowledge, the current funding is restricted essentially to a few university professors through the National Science Foundation. The rest of it is being occasionally supported from various agencies to stay engaged in activities like the research reports, which you've heard about, but most of the other work that's being done is being done through supportive philanthropic organizations or for free on weekends and evenings by scientists who are interested in these things. It probably is bounded by less than $1 million a year. It could be a few $100,000 a year of supported research directly for geoengineering. That's to my knowledge. I don't really know what
Any other panelists want to weigh in on that question? Dr. MacMartin?
The National Center for Atmospheric Research has been providing computer time, which is supported by the NSF, but that's basically, Phil's answer is correct.
And so I would guess that, and I don't want to presume anything, but it sounds like you would agree that the topic has not been adequately pursued in the research phase.
Right. My reaction is that it's very easy to identify the fact that a very small amount of effort has been put into this area, and that progress could be made much more rapidly with a relatively small amount of funding.
It leads me to ask, why has geoengineering not received the same kind of funding as maybe some other types of research over the last 8 to 10 years? Dr. Rasch?
Well, I think there's a recognition by all that it's quite a controversial subject of real concern to citizens of the U.S. and to other scientists as well, and there's some reluctance to take the first step, is my sense. That's my best answer.
Well, Dr. Majkut, or actually anyone in the panel, outside of the federal government and you've mentioned some of the philanthropic supporters of geoengineering research, what's the post-secondary education or university level of research in this area? Ms. Wanser?
I'm already on, sorry.
Yeah.
So the overall philanthropic funding in this area is, I would characterize it as maybe in the range of $1 to $2 million a year, mostly allocated towards one program, the Stratospheric Aerosol program at Harvard. For the most part, my experience in the philanthropic community is that this subject matter is not not yet acceptable for funding. So traditional sources of environmental and climate research funding in the philanthropic community are not yet funding in this area.
And Dr. Majkut, how about universities?
Well, we know there's a few research programs around the country, Harvard, University of Washington, other individual scholars. Whether or not this particular item falls under a research priority for a particular university, I don't think is a question that's easy for me to answer. There are individual academics who put their energy into it, as Phil says, but it's not a very large field. As you go to these scientific meetings where geoengineering is discussed, you see that there's a relatively small number of people working on these issues.
Are other countries working on geoengineering research? Dr. MacMartin?
So I think the largest program in the world is probably the one at Beijing Normal University in China, but that's relatively new and unclear exactly where they're going with that. But in Europe, there's some small efforts as well, but not substantially larger than what's in the U.S.
So if thinking of it in terms of global competition, it doesn't sound like we're falling behind global competitors. It's just that we're not advancing as rapidly as perhaps many or some would like. Is that fair to say?
Not yet, but that may change depending on China's future investments.
Depending on what Beijing Normal does, yes. Dr. Rasch?
Well, it was just, I might beg to differ a little bit with Doug, that my sense is that over the last 5 years or so, a variety of European countries have identified explicitly some funding for geoengineering research that amounts to a few $1 million a year, perhaps, for at that level, which is substantially larger than the amounts that I could identify in the United States.
Well, again, thank you, all of you, for being here. And my time has expired, and I recognize the ranking member of the Environment Subcommittee, Ms. Bonamici.
Yeah, thank you, Mr. Chairman. And just to follow up on the chairman's questions about work being done internationally, were any of you at the conference in Berlin? Yes. So in terms, I know the chairman mentioned global competition, but we also need to, I think, have a conversation with the concerns, and Dr. Rasch, you recognize, I mean, this, as our constituents do, there's some controversy and we need some ethical discussions and boundaries. And Dr. Majkut, you mentioned that there's a statute in the United States that research needs to be reported and there needs to be some framework. So how much work is being done internationally on collaborating on some of these questions of what are the frameworks and what are the ethical considerations and how much is regulated in terms of climate doesn't know political boundaries, so somebody in the United States has to comply with this law. But what about internationally? Who's leading that discussion?
So there are several kind of newer organizations that are looking at the international aspects of this research, and also geoengineering more broadly as something that might be used to prevent climate risk. None are represented here today. I think those discussions are beginning to occur. But it's, they're consigned to issues that are related to, but not just scientific, right? So the moral and ethical frameworks in which we look at these questions. Those conversations are beginning at still early stage.
And how does the United States compare with other, you mentioned China, Russia, other countries that are maybe working on this? In terms of having some sort of regulatory framework or guidance and ethical considerations?
Couldn't say about the foreign countries, sorry, but the United States, I think, as I testified, has a framework in place for any research that's going to take place in the next few years, and because of the strength of our scientific community and the National Academy of Sciences, I expect that we will remain at the front of figuring out how we can go about this research judiciously.
And Dr. MacMartin, we've heard today a few times that geoengineering is not going to be the magic bullet or a fix. It's not a substitute for mitigation and adaptation. And you said that geoengineering could be part of the strategy. So could you please talk about the range of activities that would be included in mitigation and adaptation, and what mitigation work is still required to prevent the most catastrophic consequences of climate change, and what role might geoengineering play in that in terms of priorities?
So I think it is clear that we eventually have to get to zero emissions or net zero emissions of carbon dioxide principally. Basically, when we hit zero is when we stop making the problem worse. And the question really is how fast that happens, because we can't do that overnight. That would have serious economic consequences if we tried to do that instantly. And so the question in some sense is how do you balance the needs of our, basically, how do you balance the needs of our grandchildren to have a safe environment and to have a decent economy? So the best efforts at mitigation are still probably going to result in some serious climate damage. You can imagine using carbon dioxide removal in the long term to pull the CO2 levels back down, and in the interim, potentially thinking of solar geoengineering as a way to keep the temperatures from getting too bad so that you don't do things like lose parts of Antarctic ice sheets in the while you're waiting for the CO2 removal to bring us back down.
Does anybody else want to add to that? The question of, we know there's a lot of interest in exploring geoengineering, but what are the mitigation and adaptation activities that perhaps need to have priority?
Well, we know that, or our sense is that mitigation and adaptation are both beneficial today. The question of geoengineering is if it will be beneficial in the future. Yeah. They're very different by nature. Reducing emissions permanently reduces the net impact of humans on the climate. Potentially introducing these technologies at some later date will do that temporarily, but their nature is very different.
Dr. Rasch?
If I can follow up, it's just to affirm what Doug MacMartin said, which is essentially, I think many of us view these sunlight reflection methods as being an interim solution, which allows, provides some breathing space while the mitigation and adaptation measures take place. And I think we all believe that they should occur as rapidly as possible. Lots of us are hoping that the carbon dioxide removal methodologies will be economically viable and provide a mechanism for drawing some of the CO2 out of the atmosphere. So that's a very important strategy to consider.
Thank you. My time has expired. Thank you, Mr. Chairman.
Thank you. The chair recognizes Mr. Weber, the chairman of the Energy Subcommittee from Texas.
Thank you, Mr. Chairman. I appreciate it. Dr. Rasch, in your testimony, you said you'd been kind of looking at this field in about 10 years, and you'd published 20 papers, or maybe it was in your comments before your testimony as I read through it. And then you also cited another gentleman that had published 42 papers. And what was his name?
Ben Kravitz,
okay, and
another colleague here at PNNL working with me.
And how long has he been in the field?
He, probably 10 years as well. He started as a PhD student working for a very eminent professor who chose to support him to work in this area based on his work on volcanic eruptions, because this is a related, the impacts of volcanoes are related to the ones we're exploring today.
Right. So the theory and concept of geoengineering is not new in the scientific community. Would you say it's just kind of taken off in the last 10 years?
Well, it's interesting. You can go back to the 60s and find conversations that have been occurring about geoengineering. It certainly started to receive a huge amount of attention following a paper that was published by a Nobel Prize-winning chemist named Paul Crutzen in 2006. So it's about 10 and a few years old. And in fact, that scientist in that paper was what brought me into the field, and it might have been some of the other people on this committee.
And is Paul Crutzen, what country is he from?
He has spent the last 30 years or so in Germany. He did have a position at my former institute, the National Center for Atmospheric Research in Colorado, and he's originally from Holland.
Okay, not that you know that much about him.
I didn't quite know how to answer. Sorry.
Well, we only have 5 minutes, so. So he published the paper, and you got interested. Is he still active in this field?
He is engaging. He's in his late 80s and ill, so he's not as heavily involved, but he does actually endorse the importance of doing research in this area to this day.
Okay. So as we've heard today, research has been moving kind of slowly, and of course, you just described the last 10 years, I guess. So how do you get that idea out there to make more people interested in it? In your opinion, what steps could be taken to increase the participation of researchers while encouraging experiments in geoengineering? What needs to be done?
Well, I'm a strong advocate for this coherent research program that involves a set of 5 elements, which I've listed in my written testimony.
Okay.
And which I'd be happy to discuss more.
Okay. So much of what we know today is based on computer climate modeling. So how would small-scale field experiments improve those models, and can you describe a small-scale experiment?
Sure. You saw some examples of some of the elements of a small-scale experiment on the slides that Wanser showed. And
okay. Did y'all collaborate on those?
We have been working together.
Good.
I'm part of that marine cloud brightening team that's located at the University of Washington, where I also have an appointment.
Okay.
So it would involve seeing whether we could, let's see, let's talk about marine cloud brightening for a moment. It would, that one, we know it is possible to make clouds more reflective, but it only happens in certain circumstances, and we're very, it's very difficult to be precise about the circumstances that it can occur in. So what we would like to be able to do, first off, there are many variables that take place which could help to explain that. The weather situations when in clouds could be part of it. We see these clouds form in the wake of freighters, which have different technologies on board. They use different kinds of fuel. They use different emissions.
Well, that's kind of fascinating because those emissions that come from those freighters is producing a heat content, perhaps carrying CO2 obviously with it. And so you're saying that that in and of itself produces droplets that intermingle with the cloud.
It's actually the particles that come out. If the emission controls on those ships were perfect, then they probably wouldn't be producing these ship tracks. What happens is that every cloud drop wants to form on a particle, all cloud drops in the atmosphere. And these ships release some particles, and when they do, those particles act to allow more clouds, more drops to form in certain clouds.
And so you can duplicate that process.
That's part of it. So what we would like to see is if we can do it in precisely the circumstances, because I was saying as ships, one ship is different from another, and it's very difficult to be precise about exactly what the conditions were that allows the brightening to occur. And we would like to be more precise about those things.
Okay. All right. Well, my time has expired, Mr. Chairman. Thank you.
Thank you. The chair recognizes the ranking member on the Energy Subcommittee, Mr. Vesey from Texas.
Thank you, Mr. Chairman. In addition, and this is for all the witnesses to answer, in addition to the solar radiation management, one alternative climate intervention strategy that the National Academy has examined recently is carbon dioxide removal. What is the potential of carbon dioxide removal to play a significant role in our efforts to mitigate the effects of climate change?
So there's a number of ideas that have been suggested, including bioenergy with carbon capture and sequestration. So basically, you grow crops, you burn them in a power plant, you suck the CO2 out of the flue gas and store it underground. And the problem with ideas like that is that the scale that you need to do them on to make a dent in climate change is something of order the scale that we're currently emitting CO2 at, which as a species is about 40 gigatons per year. And so unless you're talking about pulling, 5, 10, 15, 20 gigatons per year out of the atmosphere, it's a pretty small dent. And the problem basically is that things like the bioenergy with carbon capture and storage would compete with land use that we use for food crops. And then there's another set of ideas to directly capture it from the atmosphere, directly capture CO2 from the atmosphere. That is almost certain to be technically feasible, but right now probably too expensive. And it's almost certain to be cheaper to not put it in the first place than to take it out after you've put it in. And then there's a variety of other ideas that are probably less well understood. So the bottom line is all of the things need either we need something that is scalable, cost-effective, and does not have substantial local impacts. And right now, we don't have any ideas that satisfy all three of those, which is why we would need more research in that. And if we don't start now, it's not going to happen.
I would add to that list genetically engineered organisms and plants that might more efficiently capture carbon in the way that nature does, but in an accelerated fashion. Some of the new capabilities with genetic modification, the CRISPR technologies, may be relevant for investment in this area. I would also say that carbon removal capabilities at scale, many of them carry serious ecological consequences that also need to be evaluated as we look at them.
Another controversial area in the Congress, the GMOs. Some of the riskier strategies for carbon dioxide removal include ocean iron fertilization and the large-scale enhanced weathering. What are the drawbacks to these strategies in an environmental and public health context?
Well, those technologies, could prospectively capture quite a bit of carbon dioxide from the atmosphere and retain it in places where it would be durable, either the sea or in rocks. But the issue, as Doug says, is to do this in a way that's going to significantly affect how much excess CO2 is in the atmosphere. It's going to take a lot of land or a lot of ocean, and the ecological effects of either of those things is not quite known.
Also, I wanted to talk with you briefly about funding levels. I'm very concerned, as a lot of people are, about federal R&D programs under this administration. We saw in the budget proposal earlier this year, the Trump administration supports very large cuts to research agencies. For example, the proposal included major cuts to climate modeling and Earth system sciences at the DOE. Would these funding cuts hurt or help us better understand the field of geoengineering?
So I think it's important to acknowledge that if we're interested in engineering the climate system, that our capabilities for observing, analyzing, and interpreting the information about the climate system are essential. So all of the platforms and capabilities and talent that we have are not only areas that we want to preserve, but if we're interested in active intervention in the Earth system, we would want to advance and enhance those capabilities.
Yeah, I would just second that. We need the same climate models. We need a lot of the same observational capacity, and we use the exact same high-performance computing.
Okay. Thank you very much, Mr. Chairman. I yield back my time.
Thank you. The chair recognizes the gentleman from Florida, Mr. Posey.
Thank you, Mr. Chairman. Thank you for calling this very interesting hearing, and thank the witnesses for their informative testimony. Do you believe, this for anyone on the panel, for all on the panel, there's a risk that in starting to build geoengineering capabilities, we could lose control of them, and how do you think it would compare to the risk of bioengineering and nanotechnologies?
I'm willing to take a stab at it. I think scientists are all concerned about the possibility of this us losing control of it and adopting it. But I personally feel that it works better to operate from a position of knowledge about it rather than the absence of that knowledge. And I think the cat's kind of out of the bag at this point in the game that the technology is possible. So I would prefer to be spun up on what it's.
Okay. Ms. Wanser, you had your hand up next.
Well, solar climate engineering technologies actually have a high barrier to entry. So they're relatively expensive to engineer and relatively expensive to measure. And they scale linearly. So you evolve solar climate engineering technologies with the number of dispersals you have. They're very easy to see and detect. Whereas nanotechnology and bioengineering techniques have very low barriers to entry. You can now buy a kit to engineer organisms with CRISPR for less than $200, and you could release them into the wild. So the challenge with things like bioengineering is that they are low barrier to entry and self-replicating. So in some senses, solar climate engineering actually is less challenging from a governance perspective, provided we have a framework in place. I disagree a little bit with Dr. Majkut that we already have one. I think it's part of what we would want to define in conjunction with the research program. But I think some of the challenges here are a bit more straightforward than they are in some of these other fields.
Okay. Anyone else care to comment?
Yeah, I just wanted to add, if we did put aerosols into the stratosphere at any point, the lifetime in the stratosphere is about a year or two. And so whatever we put up there is just going to come back down. That also means that if you want to maintain it, you have to constantly be putting more in. So there's less risk of it running away when you're actually deploying it than there would be for, say, a biotechnology type intervention.
Okay. Any hard evidence on the effect that subsurface activity has on the atmosphere? I mean, we know what ended the last ice age. It was an asteroid strike, which basically created a Gulf of Mexico and darkened out the Earth for many, many years, allowed it to freeze over. There are some conditions that exist here now that have the potential to recreate that catastrophe within. Some of the research I've seen at Yellowstone, big volcano in the Azores that they say will cause a 100-foot-high tsunami, you know, but your thoughts on how that may affect us?
Well, relevant to these questions, there's a volcano, Mount Agung, which is on currently a level 3 eruption watch. So we may have a natural experiment coming up should it erupt and inject sulfates into the atmosphere. Then we would see a repeat of what previous volcanoes have done and probably some cooling influence. And thankfully, the scientific community, I believe, is ready and standing by to observe that and understand the processes as best they can. That's certainly true.
If I might follow up,
Rasch?
it's to say just that the scientific community is very interested in a rapid response team for watching over these volcanic eruptions, but they are sort of assembling it as we speak, and it's not maybe quite as far along as Joe mentioned.
One last question. What have other countries done so far in this realm?
The rapid response team is an international effort. There's certainly a very large and interested part of American U.S. society, scientists participating, but that is an international activity.
Okay. Thank you, Mr. Chairman. My time has expired.
Thank you. I recognize the gentleman from California, Mr. McInerney.
I thank the chairman, and I thank the witnesses. You all have seen the legislation I'm about to introduce. Do any of you have comments about that legislation, whether you think it's useful or should be improved or anything like that? Anyone care to answer that question?
I've had only a chance to look at it very briefly and would be delighted to provide some more comments offline for you.
Okay, thank you.
I have the same idea now.
Thank you.
So I haven't read through it in complete detail, but I think in general, I'm very supportive of having the national academies involved in trying to understand exactly, basically lay out the roadmap for research in this area, as well as looking at the governance side of things.
Yes, thank you.
As I mentioned in my remarks, I'm very supportive of the notion of a National Academy study process to help define a research agenda. The community to date in geoengineering has been very small and centered in modelers with some physicists and some ethicists and policy researchers. So I believe that that process could help expand the array of disciplines that we need to look at this area and also help to build consensus about what a research program should look like.
Well, following up with that on a governance framework, what sort of a scope of organizations and individuals should be involved in the development of a governance framework?
Well, I think we should be looking at sort of all the concerned parties, right? So the scientific community plays a vital role, I think civil society should play some role as well, and I think Congress should take into consideration the idea that you might want to have a say in how these things get governed. And then going forward, we can also look at managing these types of things with international partners as well.
Okay, thank you. Ms. Wanser, you mentioned that it would take about 20 years for the technology to be deployable. Would having a research governance mechanism speed up that timeline, in your opinion?
At the moment, one of the barriers to technology development and field research is the lack of either a government framework or a social license for the work. So I think it would reduce risk for people who would fund the research and people who would enter the field to have an appropriate governance framework to allow it to proceed. So yes.
Very good. Do any of you know if there have been field tests on geoengineering that have carried out by other countries?
I'm not aware of any.
There was a brief attempt in the UK to do a experiment that was just on a tethered hose, so it was just developing hardware that didn't actually take place. And there was an attempt in Russia a number of years ago to try to do something that was a bit of a stunt, but it wasn't really scientifically accurate.
Russia and China have limitations on what their scientists are able to do in terms of geoengineering?
So the program in China right now is purely based on climate modeling and much more focused on what the impacts of deploying solar geoengineering would be. I do know from conversations with them that they're asking questions about whether the next phase of their research should involve some experimental work, but they have not yet made any decisions about that.
So we don't need to be worried about them doing large-scale deployments?
I don't think we need to be worried about anybody doing large-scale deployments, because if you want to do scientific research, the research questions are all about process uncertainties, trying to understand chemical reaction rates in the stratosphere and things like that, and they don't require large tests to do those things.
So then what are some of the key ethical questions that we should be considering in moving forward with this field of work?
I think my personal answer to that would simply be that a lot of people are very concerned about the slippery slope and whether an effort in research is eventually going to lead to deployment. And I think a lot of people are very concerned about the research effort in geoengineering detracting from efforts in mitigation. And so in some sense, the issues with ethics and governance are primarily wrapped up in involving the public participation and where we want to be going as a society in the future.
Mr. Chairman, I want another 5 minutes. I yield back.
Thank you. And Chair recognizes the gentleman from Texas, Mr. Babin.
Yes, sir. Thank you, Mr. Chairman. Extremely interesting topics, and appreciate you convening this hearing and your witnesses being here. You've already alluded to it a little bit about the safety and environmental risks of this research being proposed, and we just talked about Russia and some of the other countries and maybe deploying fully things of this nature. And you mentioned a slippery slope, Dr. MacMartin. And what do you mean exactly by slippery slope? Is this something that you mess around with Mother Nature and it may turn into something that's even worse than you're trying to fix?
I was actually referring to the societal process, the concern that if we start doing research, that eventually that's going to lead to deployment, and people might think, wait, we haven't actually decided on deployment yet.
Right.
So that's a concern that people have expressed.
Okay. But is that a concern with any of you folks that are involved in this, that we could unleash something irreversible if you continue to do this cloud brightening or the stratospheric procedure? Is that a possibility?
I think at the level that we're talking about doing things right now, as I think Joe mentioned, the changes to the planet are vanishingly small. It would be hard. It would be hard for you to notice, to even detect it if you didn't know it was happening. So it's really tiny compared to, for example, the impact that flying an aircraft from Washington, D.C. to Seattle would have on the planet. So they're small today. If one wants to get to the point of considering having a climate-altering effect, then the impacts get much more important to worry about, and we have to be more careful and when things get ramped up to that time.
Right.
As Kelly mentioned, I think it would take 20 years to decide on whether we have a good enough understanding to decide that it might be useful to do this or not if we're going all out on it, I think.
Right. Thank you. Anybody else want to add to that?
Yeah, I think I would just reiterate that a lot of the sort of smaller scale field experiments that scientists are presently proposing to do are going to be unnoticeable to the untrained eye. You need a really fancy experimental setup and cool instruments to even detect that it's going on, right? Questions of, does this research affect sort of other societal questions about how we address climate change are real. But I think it's a bit of speculation to say whether that'll cut one way or another. We should go about this judiciously and carefully and slowly and with an open and transparent process. I think that's probably the best approach.
Okay.
I agree.
Yes, ma'am.
I think one of the things that may be helpful from a governance process or an oversight process is a definition of what we mean by research scale or small scale experiments, and then lots of transparency with regard to that, so that where it's not easy for people to understand what the limits of these things are, we have some very bright, shiny lines between what we do for research and the kinds of things that would have greater impacts.
Okay, and while you're at the mic, you discussed the need for a research framework earlier in this field, and could you explain what your whole systems approach to geoengineering research would be?
Well, probably not terribly briefly, but I think it's what's sometimes referred to as a transdisciplinary field. So we think about certainly the climate research part of it. We have a technology innovation component. We need to think how systems would interact together and how different actions taken on the Earth system would interact, like policies that we make that change the forcings in the climate too. So part of a research program is to bring people who are not currently present into the discussion, starting with aerosol engineers and other types of engineers who would be needed to think about how these things would actually work. Looking at the innovations in observations, measurement, and computing. So today, the experiment that I showed you about marine cloud brightening, they do observations like that now of pollutants. And when they go out and take those measurements, they bring them back. They take months to analyze the data. If we're acting on the Earth system actively, we're going to want information much faster, and we're going to need to improve our systems to do that. So when we think about the whole system, we have to think forward a little bit about what we'd be looking at in terms of the feedback to the perturbations that we make and how we need to understand them. Does that help?
Yes. Yes, it does. Thank you very much, and my time has expired, Mr. Chairman. Thank you.
Thank you. The chair recognizes the gentleman from New York, Mr. Tonko.
Thank you, Mr. Chair, and thank you to our impressive panel of witnesses for joining us today. As the only New Yorker on the committee, I would like to take a moment to give special thanks to Dr. Douglas MacMartin from Cornell University. We thank you for your time and your expertise, and we thank Cornell for the contributions it makes. The recently released 4th National Climate Assessment Climate Science Special Report represents the scientific collaboration of some 13 United States federal agencies with sign-off from the White House. That report found with high confidence a likely human contribution of well over 90% of the observed change between 1951 and 2010 in the global climate. Furthermore, the report found with very high confidence that the magnitude of climate change beyond the next few decades will depend primarily on the amount of greenhouse gases emitted globally and on the remaining uncertainty in the sensitivity of Earth's climate to those emissions. We know the harms caused by climate change are grave and that they are growing. They have already done harm to human health, to water quality and availability, sea level rise, and they have worsened natural disasters. For this and countless other reasons, failure to address climate change will result in significant economic harm to our country and her people. Given the conclusions of these impartial scientists and the widely accepted consensus that climate change is real and primarily driven by human activity, I urge all members of this committee to move forward with this White House-approved consensus in mind. Geoengineering absolutely should be a part of the discussion of solutions, but with that said, we can't lose sight of the fact that significant reductions in GHG emissions are indeed necessary. So for all of our witnesses, you have emphasized that numerous gaps remain in the scientific understanding of geoengineering technologies. Can each of you just briefly describe these gaps in the scientific understanding of geoengineering strategies?
Yeah, I'll mention one or two because I could go on for the whole 5 minutes. So
one or two will do.
Okay. So we at the moment don't, the situation of using geoengineering differs from either the marine cloud brightening or volcanoes, because we would intend to put particles into the atmosphere continuously rather than they would just occur episodically. And we don't know how the existing particles will respond to the to putting in these kind of particles for long periods of time. Models tell us that it will be different from the way it would work for a volcano, let's say. So that would be one example of something which we don't know, but we need more information on.
Okay. Thank you. Doctor?
One particular aspect of this that really fascinates me is questions of when you have these sort of compensating mechanisms of warming at the surface and cooling in other parts, either concentrated parts of the atmosphere or high up in the atmosphere. What are going to be the effects on other conditions that we care about, not just temperature, right? So biology, the oceans. I think a lot of these downstream issues need to be investigated much further.
Thank you. And Dr. MacMartin?
So I would second both of those and just reiterate that we know a fair amount about stratospheric aerosols just from observing volcanic eruptions, but it is different from a large volcanic eruption. We don't actually have any observations of geoengineering, obviously, and so we sort of have to figure out as we go, how do we go collect that knowledge about what the processes in the stratosphere are going to be.
Okay, thank you.
Well, we don't yet have any technology for producing aerosols of the type and at the scale that we're talking about for this. And until we know what the limits of those technologies are, what we're inputting to our models is very much guesswork. Okay. And we also don't know how to measure and detect in real time.
So then what would the next steps be to address these gaps? Any recommendations to the committee?
So I think one step is clearly to actually just start with saying, if we want to support informed decisions in 10, 15, 20 years, to be very careful about writing down what all the uncertainties are and propagating those through the climate models. So if there's something uncertain about stratospheric aerosol microphysics or chemistry, how important is that in terms of influencing our decisions, and therefore what experiments would we need to do to help resolve those uncertainties? That's the type of research that I think we need to be focused on.
Anyone else in that regard?
Yeah, I mean, I will just say that there are, I think one of the things that is missing so far is that the research that's been done today is primarily curiosity-driven, and people have picked at various elements of the geoengineering unknowns, but I think we need to do it in a much more systematic way to try and move pretty quickly towards getting an idea about what are the trade-offs involved in this work.
Okay. With that, I yield back, Mr. Chair.
Thank you. The chair recognizes the gentleman from Illinois, Mr. Foster.
Thank you, Mr. Chair, and thank you for holding this hearing. It really shows a level of engagement on this issue that I think is overdue and very welcome. Are there any sort of zero-order either cost estimates or estimates for the amount of aerosols that you'd need, for example, to reverse a 2-degree warming, or a calculation of, if you have a gigaton of coal, how many gigatons or tons of aerosols you have to put into the atmosphere? Are there any rough estimates based on volcanoes and similar that people have done?
So I'll give you a rough estimate that 1 degree Celsius of cooling, so 1.8 Fahrenheit, is, say, 10 megatons of sulfur dioxide into the upper atmosphere. And in terms of cost, there's estimates of cost that are in the billions of dollars, but quite frankly, I don't think that the direct economic costs of bringing material to the stratosphere, those probably are not the reasons why we would, how we would evaluate this. It's far more a question of what the risks and the side effects are.
Right, okay, so it wouldn't be the direct cost of actually even carrying this out. They're all would be dwarfed by, the trillion-dollar scale effects of, real climate.
Yeah, and the direct cost of doing it is probably more observational capacity of satellites and things to monitor things.
Yeah, which brings me to the issue of international governance. Because it's, Congress can pass all the laws we want, and if, China decides that it wants to preserve its islands it just built in the South China Sea, or, Bangladesh or Micronesia decides that they're going to be underwater in short order, their interests are not necessarily aligned with ours. Or if you do this and you see it's going to redistribute rainfall globally, or reverse the Gulf Stream, or stop the Gulf Stream. There are worries like that are out there. And so it seems like you need an international mechanism for someone who will say, no, you cannot do that. And, we're in a tough situation right now because we have an administration that's done things like reject the Paris Agreement. And so I was wondering if there are serious, maybe outside this country, serious discussions of how we're going to regulate this internationally.
Discussions are beginning, but as we kind of see here today, this is a new topic for conversation, particularly for a lot of policymakers. So they're sort of at their early stages. I highlighted in my testimony some ideas, and would be happy to follow up with you about them more in detail, about how we can accomplish some of these questions here and sort of build a national governance model that could influence how things work internationally. I think that would be a good thing to talk about. But yeah, we're still at very early stages in terms of international issues.
Now, it also seems to me that the level of controversy having to do with CO2 removal strategies is much lower than albedo modification, particularly atmospheric. Is that a fair reading of sort of the attitudes you see toward this? That the objections of CO2 removal are it's simply going to cost a lot more than averting the emissions in the first place.
So in terms of direct climate impacts, then there's basically no climate impacts from pulling CO2 out. That solves the root of the problem. But I think one of the reasons there hasn't been any pushback is perhaps people don't quite get what the local impacts might be. So if you need to displace land area the size of India for food crops for bioenergy, I think that would actually have some serious consequences. So I think, yes, people are less concerned about CDR, but maybe they should be a little bit more concerned than they are.
Okay. That would be a very technology-specific thing.
But very, very specific to the technology.
Yeah. And so now, when you get these sort of natural experiments from volcanoes going off, how frequent are volcanoes that actually provide you relevant data and get enough aerosols up in the stratosphere that you actually get a useful volcano? Do they happen once a decade, once a century, or once every few years?
Probably less frequently than once a decade and more frequently than once a century. They come along.
Okay. All right.
And they do have smaller scale volcanoes. One went off in Iceland a few years ago that was useful for understanding some aspects of, for example, the way clouds could be brightened by addition of extra particles in the atmosphere. Yeah. But the really big eruptions like Pinatubo or Gung, those are
rare. Yeah, and I remember after that volcano happened, I called up Nathan Myhrvold, who you're probably well aware is one of the people of means interested in paying for this. And yeah, he indicated that it simply didn't put enough into the high stratosphere to be a useful.
For the stratospheric aerosol
For the
analog, yeah.
Right. But now, if you look at the historic record of just...
Gentleman's time's expired.
Oh, excuse me. All right. Yield back.
Thank you, Mr. Foster. Appreciate that. Chair recognizes the gentleman from Indiana, Mr. Banks.
Thank you, Mr. Chairman. Very interesting discussion today. Thank you for being here. I believe, like probably most of my colleagues do, that it's imperative that we deal with the reality of a $20 trillion national debt. Even though that debt is driven by mandatory spending programs, our constituents at home expect us to find savings wherever possible. We've seen in my home state of Indiana the innovative utilization of public-private partnerships to overcome this dilemma. One example I'd like to point to is the Indiana Biosciences Research Institute. The institute is a public-private partnership between universities and research institutions, industry, and the state of Indiana. The institute fosters collaboration between these entities and life sciences research and support the commercialization of their research. One big advantage, in my view, of an arrangement like this is that the participation of industry ensures that research will be directed toward endeavors that are commercially viable and produce a positive return on investment. So with that, I'd like to hear the panel's perspective on the potential for public-private partnerships to advance research in this area. I don't know, Dr. Rasch, if you could respond to that first, would appreciate it.
Well, I know that my laboratory is quite interested in these public-private partnerships. I have to admit I'm not an expert in the area and can't tell you about the potential for this particular application, unfortunately.
Okay. And next to you.
I would also have to demur. I mean, I think public-private partnerships are useful in many contexts, but it's hard for me to state strongly one way or another on this issue.
Okay. Ms. Wanser, I see you raising your hand.
So I see tremendous opportunity for public-private partnerships in the disruptive innovation that's happening in remote sensing and in computing. So for the types of capabilities that we need to monitor and interpret what we would do in geoengineering, there are particular opportunities to work with those companies to do things in a way that's potentially an order or 2 orders of magnitude less expensive than we do it now in satellite observations, in ocean observations, the opportunity to have much more comprehensive Earth coverage and a much more granular level. And at the same time, I think there are big opportunities for partnerships in the computing space, for the adoption of cloud computing, for some of the workloads that we do in this area that could be done on the public cloud in a cheaper and more agile way, and opportunities to explore exascale computing for the kinds of things we haven't solved yet in terms of understanding the Earth system more rapidly.
So you agree that public-private partnerships are fruitful, but do you believe that the environment exists to further public-private partnerships as it stands today?
My experience leads me to believe to be hopeful, yes.
Okay, thank you. I yield back.
Thank you. I thank each of the witnesses for being here today, and very interesting committee hearing, and appreciate the members and their questions. The record will remain open for 2 weeks for additional written comments and written questions from members, and this hearing is adjourned.